Okay, imagine this. You're finally buying that concert ticket online, you hit purchase, and the website just dot hangs. you know, or maybe you're tracking a live score and the numbers jump around in a way that simply doesn't add up.
Right.
It feels like digital chaos, doesn't it? Like data's just going completely rogue.
Hmm.
Well, today we're taking a deep dive into the unsung heroes that quietly save us from this kind of mayhem: database transactions.
Yeah, you've really hit on the core problem there. Our mission today is to, cut through the jargon and truly demystify these critical concepts.
Okay.
We want to reveal how transactions simplify the programming model for you, the developer, and how they protect your valuable data from what can only be described as, well, the harsh realities of potential software failures, hardware crashes, network interruptions, and all sorts of tricky race conditions.
Right, all the things that can go wrong. So we're going to unpack why transactions were even conceived in the first place. We'll explore what that famous ACID acronym actually means, and believe me, it gets surprisingly tricky.
It really does.
Then we'll look at the various ways concurrent operations can completely mess up your data. And finally, how different levels of transaction isolation attempt to keep things sane, often with some truly unexpected trade-offs.
Exactly. By the end, you should be incredibly well informed on these critical choices and maybe even some cutting-edge solutions that ensure your data's integrity.
Okay, so to truly grasp the genius of transactions, maybe we first need to confront the sheer number of ways data systems can just, well, utterly fail.
Yeah, it's kind of sobering when you listen out.
Think about it. The database software itself might crash mid-write, or maybe the hardware just gives out. Your application could go down halfway through an important operation.
Network connections, too.
Exactly. Network connections are notoriously unreliable. They can sever mid-update. And then there's that silent, insidious problem: multiple clients writing at the exact same time, totally overwriting each other's changes, or even worse, reading data that's only been partially updated, making no sense at all.
Right, these are the harsh realities we're constantly facing in software development.
And these harsh realities are precisely what transactions were designed to tame.
For decades, yeah.
Yeah.
They've been the primary mechanism for simplifying these issues. The core concept is, I think, deceptively simple.
Right.
You group several reads and writes into a single logical unit.
An all or nothing deal.
Exactly. It's all or nothing. Either the entire transaction succeeds, which we call a commit, or it fails, which means an abort or a rollback.
Right.
Everything gets undone.
And for us, the application developers, what's the biggest simplification that brings to error handling? I mean, how much of that complexity does it truly abstract away?
Oh, it's a game changer. Seriously.
Mm.
With transactions, you often don't have to worry about those partial failures.
Mm-hmm.
If a transaction aborts, you have this rock-solid guarantee that absolutely nothing has changed. It's as if the transaction never even happened.
Okay.
This simplifies error handling immensely because it allows you to safely retry the whole operation from a clean slate
Yeah.
without wondering what state things were left in.
It's kind of amazing how long this core idea has been around. Transactions aren't some law of nature. They're a design solution, dating way back to IBM System R in, 1975?
That's right, a long history.
Yet in the late 2000s, with the rise of non-relational or NoSQL databases, we saw this dramatic shift. Transactions were often abandoned or completely redefined. It led to this popular, almost dogmatic belief that transactions were basically the antithesis of scalability.
And this created a real battleground, didn't it?
Yeah.
We had vendors on one side saying, transactions are always essential for serious applications with valuable data, while the NoSQL crowd countered with transactions are always bad for scalability, like it was black and white.
Which is rarely true in tech.
Almost never. Both extremes are hyperbole.
That's a crucial point, because it highlights how much misunderstanding there can be. So how does that principle of understanding trade-offs apply to the most famous concept related to transactions: ACID?
It applies directly. The truth lies in understanding the advantages and the limitations of transactions and the specific trade-offs involved for your situation. No single viewpoint is always correct. You have to look deeper.
Okay, so now that we've seen the chaos transactions aim to solve, let's unpack the legendary four letters that promise order: ACID. Atomicity, consistency, isolation, and durability. Coined back in 1983. Sounds like a pretty solid foundation, doesn't it?
It does, but here's where it gets really interesting and maybe a bit messy. In practice, one database's implementation of ACD doesn't necessarily equal another's.
Uh,
There's a lot of ambiguity, especially around isolation, which we'll definitely get into. So when a system claims it's ACID compliant, well, it's often more of a marketing term than a precise technical guarantee.
right. So for you, the listener, this means it's crucial to understand what guarantees you can truly expect beyond the buzzword.
Absolutely. You need to look under the hood.
Let's break down each letter then, starting with atomicity, the A. What's its core purpose? Is it about concurrency?
Surprisingly, no. Atomicity in ACID isn't primarily about handling multiple concurrent operations. It's really about fault tolerance for multi-step operations.
Okay, explain that.
Think of it this way. If a fault occurs mid-transaction, say your application crashes or the network drops, and the database can't complete all the writes it was supposed to, then all the prior writes within that transaction are discarded or undone.
Ah, rolled back.
Exactly. The system is guaranteed to be either in the state before the transaction started or completely after it's successfully committed. Never in some half-finished, unknown, possibly corrupt state.
So it's not about preventing concurrent access, but about ensuring a clean slate if something goes wrong in the middle of a complex operation. That's why some suggest abortability might be a more fitting term, maybe.
That's a great way to put it, abortability. It ensures that if an error happens halfway through, you're not left guessing about what changes actually took effect and what didn't. Atomicity means you can safely retry, because it's as if the previous failed attempt never happened at all.
Okay, that makes sense. That brings us to consistency, the C. Now, this one sounds like a database property, but is it really? What's the crucial insight for developers about where consistency truly resides in an application?
That's a fantastic question, because the word consistency is, frankly, terribly overloaded in computing. It means different things in different contexts.
Right.
In the context of ASIC, it traditionally refers to the idea that the database should always be in an application-specific good state. Think about your business rules or invariants.
Like accounting, debits, and credits balancing.
Exactly like that. In an accounting system, credits and debits must always balance. That's an invariant. But here's the aha moment for you. You, the application developer, are actually the one responsible for defining and preserving these invariants through your transaction logic.
So the database doesn't enforce my business rules.
Not directly. The database stores your data and provides the AI and D properties, but it can't prevent you from writing bad data that violates your own application's business rules, as long as it meets basic constraints like data types.
So the database ensures atomicity, isolation, and durability, and my application uses those guarantees to achieve its own notion of consistency.
Precisely. You leverage A, I, and D to make sure your transactions maintain your invariants. So you could argue the C doesn't truly belong in ACID as a database guarantee in the same fundamental way A, I, and D do. It's more of a property of your application that relies heavily on the database's other properties.
Interesting distinction. Okay, next up, isolation, the I. This one is focused on concurrency issues when multiple clients access the same data simultaneously. The formal definition is often cited as serializability.
Right. Serializability means that the database guarantees that even if transactions run concurrently, the result is the same as if they had run one after another, serially, as if no concurrency were happening at all.
That sounds like the ideal solution. Why wouldn't everyone just use that?
It certainly sounds perfect, doesn't it? But here's the catch. True serializability is rarely used in practice because historically it carried a significant performance penalty.
Performance again.
Always. So, many popular databases implement weaker guarantees, weaker isolation levels. These are, unfortunately, much harder to understand and, crucially, can lead to subtle bugs that are incredibly difficult to find during testing. We'll definitely dive deep into those weaker levels and their pitfalls in a bit.
Looking forward to that. Finally, durability, the D. What promise does it make for our precious data?
Durability is the promise that once a transaction has successfully committed, any data it has written won't be forgotten, even if there's a hardware fault or the database crashes later on.
How is that typically achieved?
Usually it means writing the data to non-volatile storage like a hard drive or SSD. Databases often use techniques like write-ahead logs, WAL, for this. Or it could mean replicating the data to other machines before confirming the commit. The key is the database waits for these writes or replications to complete before it reports success back to your application.
But I've heard a rather provocative thought about durability. Is it truly absolute? Can we really count on it 100%?
Not really. Perfect durability doesn't exist in the real world.
Give us some examples of how it can fail.
Sure. SSDs, for instance, can actually lose data if they're left unpowered for long periods. Firmware in drives can have bugs. Correlated faults, like a power surge taking out a whole rack, could potentially wipe out all your replicas at once if they're co-located. And data on disk can even gradually become corrupted over time due to subtle hardware issues, sometimes called bit rot, without immediate detection.
Wow. Okay. So the real takeaway for you, the listener, is that no single technique provides absolute guarantees. Writing to disk, replicating to remote machines, and having robust backups, they should all be used together to maximize your chances of data survival.
Exactly. Always take any theoretical guarantees, especially around durability, with a healthy grain of salt and plan for mitigations.
Now, when we discuss these ACI properties, they primarily come into play in scenarios where you need to modify several pieces of data, several objects at once, right? Let's think about a common relatable example, an email application.
Right. A good example. Say you mark an email as read in your inbox. That's one write operation updating the email status.
Okay.
But you probably also have an unread message counter displayed somewhere, maybe next to the inbox folder. That counter needs to be decremented. That's a second write operation, potentially to a different part of the database.
And those two have to happen together.
They must be kept in sync. If isolation is violated, you might see the email marked as read, but your inbox counter still shows the old, higher number of unread messages. This kind of dirty read or inconsistent state can really confuse the user.
And atomicity helps how?
Atomicity prevents partial updates if, say, the email status update succeeds, but the counter decrement fails midway due to a crash. The whole operation would roll back.
We see this need for multi-object coordination everywhere, don't we? In relational databases, you have foreign keys that need to ensure linked data remains valid when you delete or update something.
Absolutely. Or in document databases, if you choose to denormalize data for performance storing related information together, you then have the burden of updating multiple documents whenever that information changes to keep everything consistent.
Even secondary indexes. When you update a piece of data, the indexes pointing to it also need to be updated. That's effectively writing to different database objects that need to be perfectly coordinated with the main data change. It's a constant dance.
It certainly is. And it's also important to note that atomicity and isolation apply even to single object changes, especially large ones.
How so?
Well, imagine your application is writing a large 20 KB JSON document. You absolutely don't want a situation where a network glitch or crash leaves a half-finished, unparsable fragment of that JSON in the database. Storage engines almost universally provide atomicity and isolation at the single object or single page level for precisely this reason.
Okay, that makes sense. And this leads to some potentially misleading terminology sometimes. You might hear about atomic operations like increment or compare and set for single objects. What's the distinction between these and what we're calling a full transaction?
That's a really good point to clarify. Those single object atomic operations, like INCR in Redis or compare and set, are incredibly useful for preventing lost updates on individual items. But they are not transactions in the usual ACID sense, despite sometimes being marketed as lightweight transactions or even just ACID.
So what's the fundamental difference?
A transaction, in the ACID context we're discussing, is fundamentally about grouping multiple operations on potentially multiple different objects into one single, indivisible, all-or-nothing unit. Those atomic ops usually work on just one thing at a time.
Okay, good distinction. Now, thinking about when things go wrong, what's the single most valuable feature that transactions give developers?
For me, it's the ability to abort and safely retry if an error occurs. ACID databases are fundamentally built on this philosophy. If there's any risk of violating atomicity, isolation, or durability, the database would rather abandon the transaction entirely, abort it, than allow it to remain half-finished or potentially inconsistent. And this reduces a huge class of potential errors down to a simple try again from your application's perspective.
Yeah.
That simplifies application logic enormously.
Yet, it's surprising how often this core benefit seems to be missed or underutilized in real-world applications. I've personally seen systems maybe using certain kinds of replication, like leaderless replication, that often work on more of a best effort basis.
Right, where the application developer has to explicitly handle and recover from partial failures themselves, which is hard.
Exactly. And even popular ORM frameworks like Rails Active Record or Django's ORM often don't automatically retry aborted transactions by default. They tend to just bubble up an exception, sometimes losing user input in the process.
Yeah.
That feels like a real missed opportunity, especially when safe retries are arguably the whole point of having aborts in the first place.
It absolutely is a shame when frameworks don't leverage that capability. And to be fair, even retrying isn't a silver bullet without its own complexities.
What are some pitfalls of retrying?
Well, first, idempotency. If the transaction actually succeeded, but the network failed while the database was acknowledging the commit, the client might think it failed. Retrying could then cause the operation to be performed twice, unless you've built application-level deduplication logic.
Okay, like double charging someone.
Exactly. Second, overload. If the error is due to the database being overloaded, blindly retrying immediately will just make things even worse. You need strategies like exponential backoff and limiting the number of retries.
Makes sense.
Third, error types. You should only retry after transient errors, things like a deadlock, a temporary network issue, or maybe a node failure in a cluster. Retrying after a permanent error, like a constraint violation, for example, a unique key conflict, is pointless. It'll just fail again.
Right.
And finally, side effects. If a transaction has external side effects, maybe it sends an email or calls an external payment service, that side effect might happen even if the database transaction itself ultimately aborts and rolls back. Handling that requires careful coordination, often using two-phase commit across systems, which is complex.
Okay, so retrying is powerful, but not trivial. Now here's where things get truly gnarly, I think. Weak isolation levels.
Uh-oh. Yeah.
Imagine two people trying to grab the last concert ticket online at the exact same millisecond. Who gets it? That split-second uncertainty, where things can go subtly wrong if not handled perfectly, is a race condition.
Right. The bane of concurrent programming.
And these are the silent, insidious bugs that are incredibly hard to track down because they often depend on rare timing issues, making them almost impossible to reproduce reliably in testing.
That's exactly why, in theory, strong isolation should make your life easier. It should let you pretend no concurrency is happening at all. Serializable isolation, the strongest level, guarantees that transactions have the same effect as if they ran one after another. Perfect predictability.
Ah.
But, as we mentioned, in practice, many databases default to or commonly use weaker levels of isolation. These protect against some concurrency issues, but crucially, not all of them.
And they're harder to reason about.
Much harder for you, the developer, to reason about. And they can easily lead to those subtle bugs you just described, the ones that only show up under load or specific timing conditions.
And these aren't just theoretical academic problems, are they?
Not at all. We've seen real-world consequences stemming from weak isolation bugs, things like substantial financial losses, companies facing investigations by financial auditors, customer data getting corrupted in ways that are hard to fix.
And it's not just obscure databases. Even many popular relational database systems, often considered ACID, use weak isolation levels by default.
That's right, which means they might not have prevented these specific kinds of bugs from occurring out of the box.
This really highlights why blindly relying on tool names or marketing slogans like ACID compliant isn't enough, doesn't it?
Absolutely. For you to truly build robust applications, you need to understand the common kinds of concurrency problems that exist and exactly how, or importantly, if your chosen database and its configured isolation level prevents them.
Okay, so let's start with the most basic common level, read committed.
Right. Read committed is the default isolation level in many very popular databases. Oracle, PostgreSQL, SQL Server, and others often start here.
What guarantees does it provide? What does it protect you from?
It offers two key guarantees. First, no dirty reads. Meaning, when your application reads from the database, you will only ever see data that has already been successfully committed by another transaction. So if user 1 starts a transaction, sets x equals 3, but hasn't committed yet, user 2's get x query will still return the old committed value, say 2.
Okay, so you don't see half-finished work.
Exactly. You're prevented from ever seeing partial updates or, crucially, data that might later be rolled back if the other transaction aborts. This makes reasoning about the data you read much simpler.
And the second guarantee of read committed.
The second is no dirty writes. This means your transaction won't accidentally overwrite data that another transaction has already written but not yet committed.
How does that help?
This prevents some potentially severe concurrency problems. Imagine Alice and Bob simultaneously trying to buy the last available car online. The buying process might require two writes. First, updating the car's listing record with the buyer's ID, and second, sending an invoice to the buyer.
Okay.
Without dirty write prevention, it's possible Bob's transaction updates the car listing first, but doesn't commit. Then Alice's transaction overwrites Bob's uncommitted change in the listing and also writes her invoice and commits. Then Bob's transaction might commit its invoice right. Now Bob thinks he bought the car, Alice has the invoice, and the car listing might end up with Bob or Alice, depending on final timing. It's a mess.
Thanks.
Read committed prevents such mix-ups, typically by using short-lived row-level locks for writes. If you try to write to a row, another uncommitted transaction is already written to, you have to wait.
Okay, so no dirty reads, no dirty writes. Sounds pretty good. But crucially, you mentioned earlier that read committed does not prevent the lost update problem. Like with two concurrent counter increments, why not?
Right, that's a key limitation. It doesn't prevent that specific lost update because the second write, the one that overwrites the first increment, happens after the first transaction has already committed its increment. So it's not technically a dirty write, it's overwriting committed data.
Ah, I see.
It's still incorrect behavior from the application's perspective. One increment is lost. But it happens because of a read-modify-write cycle, where the read step in the second transaction doesn't see the effect of the first transaction's committed write. Read committed simply isn't designed to prevent that race condition.
Okay, that clarifies the limitation. This leads us naturally to snapshot isolation, which aims to solve a different but also very common problem, read skew. Can you give us an example of how read skew might manifest?
Sure. Let's use the classic bank balance example. Imagine Alice has $1,000 spread equally across two bank accounts, so $500 in each. A transaction starts to move $100 from account 1 to account 2. Now, if Alice runs a query to check her total balance right in the middle of that transfer, using only read committed isolation, it's possible her query first reads account 1 after the $100 has been debited, seeing $400, but then reads account 2 before the $100 has been credited, still seeing $500.
So she sees $400 plus $500 equals $900.
Exactly. She temporarily sees a total balance of $900, which is incorrect and inconsistent. This is read skew. It's also sometimes called a non-repeatable read, because if her query read account 1 again later in the same transaction, it might get a different value, $500 after the credit arrives. Different parts of a single query or transaction effectively see the database at slightly different points in time.
And why does that read skew matter for you, the developer? I mean, while it's maybe just a temporary glitch for Alice checking her balance, how does it impact real-world applications more significantly?
It's actually crucial for things like database backups. A backup process might run for hours on a large database. If it's only using read committed, the data it backs up could be in a completely inconsistent state, mixing data from before and after various transactions completed during the backup window. That backup might be useless for recovery.
Ah, okay. And analytics.
Same problem for long-running analytical queries. If you're trying to calculate sums or averages across large data sets and the underlying data is changing while your query is running, you could get nonsensical results due to read skew.
So snapshot isolation is the common solution here.
Yes, it's a very popular and effective solution for these issues. The core idea behind snapshot isolation is elegant. Each transaction reads from a consistent snapshot of the database, essentially, a frozen view of the database as it existed at the precise moment the transaction started.
Like a photograph.
It's exactly like a photograph. Even if other transactions commit changes to the data after your transaction started, your transaction continues to see only the old data from its specific snapshot, its point in time. This is a huge boon for long-running read-only queries like backups and analytics. They get a perfectly consistent view without blocking writers.
And this is implemented using something called multi-version concurrency control, or MVCC. Can you briefly explain how that works under the hood?
Sure. MVCC is the mechanism that makes snapshot isolation efficient. Essentially, instead of overwriting data in place, the database keeps several different committed versions of an object, like a row, side by side.
Multiple versions of the same row.
Yeah. For instance, in PostgreSQL, when you update a row, it's internally translated into marking the old version as deleted by the current transaction ID and inserting a new version of the row created by the current transaction ID. When another transaction reads, the database looks at the transaction IDs associated with each version, when it was created, when it was deleted, and compares them to its own transaction ID and its snapshot timestamp to figure out which version of the row is visible to it.
That sounds complex but powerful.
It is. But the true genius of MVCC isn't just the multiple versions. It's how this enables a fundamental property. Readers never block writers, and writers never block readers. This is a massive improvement over older locking-based methods for read-heavy workloads. as it allows high read concurrency without sacrificing the consistency provided by the snapshot.
Okay, that's a key benefit. Now, for the fun part you alluded to earlier, the naming mess. Snapshot isolation seems like a widely adopted and useful isolation level, but you mentioned different databases call it different things.
Oh yeah, it's confusing. Oracle, for example, actually calls its implementation of snapshot isolation serializable.
Wait, serializable? But that's supposed to be the strongest level.
Right, but Oracle serializable is actually snapshot isolation. Meanwhile, PostgreSQL and MySQL historically called their snapshot isolation level repeatable read.
Okay, so why all the confusion? Is there a standard?
The root cause is that the ANSI SQL standards definitions of isolation levels, like read committed, repeatable read, serializable, are ambiguous, flawed, and were defined before snapshot isolation was even invented or well understood.
The standard is lagging behind practice.
Severely. So databases like PostgreSQL and MySQL called their MVCC-based snapshot isolation level repeatable read, partly to claim some level of standards compliance, even though it provides stronger guarantees than the standard's vague definition of repeatable read might imply. The honest truth is, as the source material puts it, nobody really knows what repeatable read means definitively because implementations vary so widely based on how they interpret the flawed standard.
So the lesson for you is don't just trust the name of the isolation level. You have to understand the specific guarantees your database provides under that name.
Precisely. Read the documentation carefully for your specific database version.
Okay, let's delve into some more of those subtle concurrency bugs.
Yeah.
We've talked about dirty writes and read skew, but what about lost updates? You mentioned the concurrent counter increments earlier failing even under read committed. How does that typically happen, and what are the common solutions?
Right, the lost update. It occurs typically in a read, modify, write cycle. An application reads a value from the database, modifies it in application code, like incrementing it or adding an item to a list within a JSON document, and then writes the new modified value back.
Okay.
Now, if two transactions do this concurrently for the same piece of data, say reading the counter value 5, both incrementing it to 6 in their application memory, and then both writing 6vinc, the final value will be 6, not 7. One of the increments has been lost.
And this isn't just counters, right?
No, it applies anytime you modify data based on its prior state. Concurrently adding different items to the same list in a JSON document, or two users editing different paragraphs of the same wiki page simultaneously and saving one set of changes might overwrite the other if not handled carefully.
So what are the remedies? How do we prevent lost updates?
There are several common strategies. Often, the best solution, if applicable, is to use the database's built-in atomic write operations. Instead of reading the counter, incrementing in the app, and writing back, you just issue a single command like update counter set value +1 where e equals 123.
And the database handles the concurrency internally.
Exactly. The database guarantees that the increment happens atomically, preventing the lost update. However, a word of caution. Some ORMs might make it easy to accidentally fall back to the read, modify, write pattern, even when an atomic operation is available, so you need to be mindful of how your tools translate your code.
What are other options if atomic operations aren't suitable?
Another common approach is explicit locking. The application can manually tell the database to lock the objects, like rows, it intends to update, usually by adding /update to the select query. This forces other transactions trying to read or write the same locked rows to wait until the first transaction commits or aborts.
But that requires the developer to remember to do it everywhere.
Yes, that's the downside. It's powerful but error-prone because it's easy to forget to acquire a necessary lock in some code path, leading to subtle lost update bugs.
No, I believe some databases offer automatic detection for lost updates, which sounds like a much less error-prone approach for developers.
Absolutely. This is a fantastic feature available in some snapshot isolation implementations. Notably, PostgreSQL's repeatable read level, which is snapshot isolation, Oracle's serializable level, also snapshot isolation, and SQL Server's actual snapshot isolation level can automatically detect when a lost update would occur.
How do they do that without luck?
They essentially let the transactions run in parallel using snapshots, but they track which transactions write to which objects. If the database detects that a transaction is trying to commit a write based on a previous read, but the data it read has since been modified by another committed transaction, meaning a lost update would happen, it automatically aborts the committing transaction.
So it prevents the lost update by forcing a retry.
Exactly. It turns the lost update condition into a transaction abort, which the application can then safely retry. This is much less error-prone than manual locking because it's automatic.
What about systems that don't have these advanced transactional features, like simpler key value stores?
For non-transactional databases, or sometimes even within transactions, you might use compare and set CAS operations. The idea is that when you write the data back, you tell the database, only update this value to X if it still has the value Y that I originally read. If another transaction changed it in the meantime, the CAS update fails, and the application knows it needs to retry the whole read, modify, write cycle.
Okay. And in the world of replicated databases, things get even more complex, right? Locks and CAS assume a single source of truth.
They certainly do. Locks and compare and set operations typically rely on having a single, up-to-date copy of the data. This assumption breaks down in multi-leader or leaderless replication setups, where different replicas can accept writes concurrently.
So what happens there?
In those systems, you often see the database detecting conflicting concurrent writes to the same item. Instead of blocking or aborting, it might store multiple conflicting versions, sometimes called siblings, and push the problem of resolving the conflict up to the application layer. Or some systems offer special commutative atomic operations, like CRDTs, conflict-free replicated data types, designed to merge concurrent updates correctly.
And what about the simpler approach?
The simpler but often dangerous approach common in these setups is last write wins, LWW. Here, concurrent writes happen, and the system simply picks one version based on timestamp or some other arbitrary rule, silently discarding the other writes. LWW is notoriously prone to lost updates.
Okay, definitely something to watch out for. Now we get to the really subtle race conditions. Right skew and phantoms. Let's set the scene with the doctors on call example from the source material. Alice and Bob are the only two doctors currently listed as on call in the hospital scheduling system. Both feel unwell around the same time and decide to go off call using the application.
Right. So in each of their separate transactions, the application logic probably first checks. Is there at least one other doctor currently on call? Because the hospital rule is you need at least one doctor on call at all times.
Okay.
Let's assume the database is using snapshot isolation. Alice's transaction starts, reads the list, sees Bob is on call, so count one. Bob's transaction starts concurrently, reads the list from its snapshot, sees Alice is on call, count one. Both checks pass.
They both think it's safe to go off call.
Exactly. So Alice's transaction proceeds to update her record, setting her status to off call. Bob's transaction proceeds to update his record, setting his status to off call. Both transactions commit successfully because they didn't directly conflict on the same row using snapshot isolations rules.
But no.
Now, 0 doctors are on call, violating the crucial business rule. This is right skew. They were updating different objects, their own records, which is why it's less obvious than a simple lost update on the same counter. But their decisions were based on the same initial read condition that there were 2 doctors on call, which subsequently became outdated by the other transaction action.
Wow, that's a great example of how these bugs can hide in plain sight. So right skew is like a generalization of the lost update problem.
You can think of it that way. It's broader. It typically occurs when 2 transactions read some of the same objects, like checking the on-call count. Then, based on what they read, they proceed to update different objects, their individual status records, under an assumption that there would still be another doctor on call that becomes false by the time the transaction commits.
And why is this so tricky for databases to handle?
It's tricky because simple atomic single object operations don't help. They were updating different objects. And crucially, most standard snapshot isolation implementations, even those that automatically detect lost states, do not automatically detect and prevent right skew.
So you need something stronger.
Yes. To reliably prevent right skew, you typically need true serializable isolation.
Where else might we see this subtle right skew pattern in the wild? What are other common examples?
Well, several places. Think about a meeting room booking system. 2 people might concurrently check if room 101 is free from 2 p.m. to 3 p.m. Both see it's free in their snapshot. Both then proceed to insert a booking record for that same room and time slot. They inserted different rows, but the result is a double booking that's right skew.
Okay, what else?
Maybe a multiplayer game where 2 players try to move different game figures to the same unoccupied square on the game board simultaneously. Or claiming a unique username. 2 users check if Kuluser123 is available, both see it is, both try to register it. Or critically, in financial systems, preventing double spending. Checking if a user has enough funds, then creating a payment record. If done concurrently without proper protection, 2 payments could go through based on the same initial balance check.
These all seem related to checking a condition and then acting on it. And what about this related term, phantoms? That sounds like something out of a ghost story.
Okay? It's a fitting name for the underlying issue that often causes right skew. A phantom occurs when a write in one transaction changes the result of a search query, a predicate, in another transaction.
Explain that a bit more.
Imagine transaction A is checking for all meeting rooms currently available between 2 p.m. and 3 p.m. While transaction A is still running, transaction B inserts a new booking for room 101 at 2:3 p.m. and commits. If transaction A were to run its search again within the same transaction, it would now see one fewer available room. That newly booked room, or the lack of its availability, is the phantom relative to the first search.
So it appears or disappears unexpectedly.
Exactly. Now, snapshot isolation actually does protect read-only queries from phantoms. Your query always reads from the consistent snapshot, so new bookings wouldn't appear. But, and this is the key point, it doesn't necessarily protect read-write transactions from phantoms in a way that prevents write skew. The doctor example is a write skew caused by a phantom. The phantom was the other doctor disappearing from the on-call list after the initial check was made.
Okay, that's subtle but crucial. Now, I read about one last resort workaround for systems without serializability called materializing conflicts. What does that involve, and why is it generally undesirable?
Right. Materializing conflicts is basically an artificial way to force a write conflict where the database's isolation level, like snapshot isolation, wouldn't automatically detect one specifically to prevent write skew.
How would you do that?
Using the meeting room example, instead of just checking for overlapping bookings, you might have a separate table that explicitly lists all possible bookable time slots, say one row per room per hour. When you want to book room 101 at 2 p.m., you'd have to acquire an explicit lock, like select for update, on the specific row representing room 101 2 p.m. slot. This forces any concurrent transaction trying to book the same slot to wait, effectively turning the write skew potential into a direct locking conflict.
But that sounds complicated.
It is. The source material describes it as hard and error-prone and ugly. Why? Because it makes your concurrency control mechanism leak into the application data model. You're adding extra tables and logic purely to work around the limitations of your isolation level, making your application more complex, and potentially introducing new kinds of bugs if you don't implement the locking perfectly. Ideally, you'd want the database's serializable isolation to handle this automatically and transparently.
This brings us nicely to the Holy Grail, serializable isolation itself. Why is it considered the strongest, most ideal isolation level?
Because it provides the simplest guarantee to reason about.
Mm.
It guarantees that even though transactions may execute in parallel for performance, the end result is precisely the same as if they had executed one at a time, serially, in some sequential order, without any concurrency.
No surprises.
No surprises. This means the database prevents all possible race conditions we've discussed: dirty reads, dirty writes, read skew, lost updates, write skew, phantoms, all of them. It's the ultimate safeguard against concurrency anomalies.
So the obvious question then is, if it's so good, why isn't everyone using it all the time? It sounds like the perfect solution.
Yeah, it does sound perfect. The answer, as is so often the case in databases and distributed systems, comes down to performance. Achieving full serializability without crippling performance has historically been extremely challenging, though things are getting better.
Okay, so what are the main approaches developers should know about for how databases actually achieve serializability today?
Broadly, there are three main approaches you'll encounter. The first, and perhaps conceptually simplest, is actual serial execution.
Just run them one at a time.
Literally, the simplest way to avoid any concurrency problems is to execute only one transaction at a time in serial order, typically on a single thread per CPU core or per data partition. This completely sidesteps the need for complex conflict detection, because there's simply no concurrent operations happening on the same data at the same time.
That might sound really counterintuitive in our modern multi-core world. Why is this approach even viable, let alone sometimes fast?
It's become much more viable since around 2007, for a couple of reasons. First, RAM became cheap enough that many systems can keep their entire active dataset in memory. This means transactions avoid slow disk I/O and can execute incredibly quickly.
Okay.
Second, many typical OLTT, online transaction processing transactions, think booking a flight, making a purchase, are actually very short and simple. When transactions are fast and run entirely from memory, executing them one after another on a single thread can actually be faster than dealing with the overhead of locking and coordination required by multi-threaded concurrent execution.
Which systems use this?
Systems like Volt DBH Store were pioneers here. Redis, while primarily a key value store, executes transactions serially. Datomic also uses a single writer approach. They can achieve very high throughput this way under the right conditions.
What's the catch for the developer using this approach?
The main catch for you is that it usually requires encapsulating entire transactions within stored procedures.
Ah, stored procedures. Those have a bit of a mixed reputation in development circles, don't they?
They certainly do. Historically, often involving vendor-specific, sometimes awkward languages. The reason they're often required for serial execution is to avoid network latency. If your application sent each statement of a transaction back and forth across the network, the round-trip time would kill single-threaded performance. With a stored procedure, the application submits the entire transaction logic, you can build check balance, debit account, credit account, record transaction, to the database in one go, and the database executes it all at once, serially, without network hops in the middle.
Are modern stored procedures better?
Modern implementations often use general-purpose languages like Java, JavaScript, or Lua, which can mitigate some of the traditional pain points of debugging and vendor lock-in associated with older store procedure languages like PL/SQL or T-SQL.
And how does this single-threaded approach scale?
Scaling typically relies on partitioning your data. If your data can be split across multiple partitions, say based on user ID, and most transactions only need to access data within a single partition, then each partition can have its own independent transaction processing thread running serially. This allows throughput to scale linearly with the number of partitions or cores.
But what about transactions that need data from multiple partitions?
That's the Achilles heel. Cross-partition transactions require coordination between the threads, making them vastly slower and often imposing a hard limit on overall system throughput. So this serial execution approach is generally best suited for applications with lots of short, fast transactions that predominantly access data within a single partition, where the active data set fits comfortably in memory.
Okay, that's approach one, actual serial execution. What's the second major approach to serializability?
The second approach is the old guard, the classic, two-phase locking, or 2PL.
Not to be confused with two-phase commit.
Correct. Good clarification for the listeners. Two-phase commit, 2PC, is a protocol for coordinating distributed transactions across multiple nodes. Two-phase locking, 2PL, is a concurrency control mechanism typically used within a single database node, though variations exist for distributed systems, to achieve serializable isolation. For decades, 2PL was pretty much the only viable option widely implemented for strong serializability.
How does 2PL work? Is it like the locks used for read committed?
It's similar in concept, but much stricter. Read committed uses short-lived locks mainly to prevent dirty writes. 2PL uses longer-held locks to prevent a wider range of anomalies. The core idea is, if transaction A wants to read an object and transaction B wants to write to that same object, B must wait until A commits or aborts. Conversely, if A wants to write an object and B wants to read or write that same object, B must wait until A commits or aborts.
So unlike snapshot isolation.
Exactly. In 2PL, writers block readers and readers block writers. Locks, typically shared locks for reading, exclusive locks for writing, are acquired as needed and are held until the end of the transaction, commit or abort. This growing phase of acquiring locks and shrinking phase of releasing them all at the end gives it the name two-phase locking.
That sounds like a stark contrast to snapshot isolation's readers never block writers philosophy.
Yep.
What's the main downside of 2PL then?
You've nailed it. Performance and concurrency. While 2PL provides full serializability and protects against lost updates, write skew, and phantoms, its major downside is significantly worse throughput and much less predictable response times compared to snapshot isolation.
Why is that?
It's due to all the blocking. Locks create contention. One slow transaction holding locks on frequently accessed data can bring large parts of the system to a grinding halt, as many other transactions pile up waiting for those locks. This leads to unstable latencies and poor performance, especially under high contention.
And deadlocks.
Deadlocks are also a much more common problem with 2PL. This is where transaction A is waiting for a lock held by B, and transaction B is waiting for a lock held by A. They're stuck in a cycle. The database has to constantly detect these deadlock cycles and then choose a victim transaction to abort and roll back, allowing the other to proceed.
Okay. And how does 2PL deal with those phantom issues we discussed earlier, where a new row appears that matches a query predicate?
Good question. To handle phantoms correctly and provide true serializability, 2PL conceptually needs something called predicate locks. A predicate lock wouldn't lock specific rows that exist, but rather lock the condition or predicate of a query. For example, if you query for all doctors currently on call, where on-call is true, a predicate lock would prevent another transaction from inserting a new doctor row with on-call true until the first transaction finishes.
That sounds hard to implement efficiently.
It is. True predicate locks generally don't perform well, so most databases that use 2PL implement a practical approximation called index range locking, or sometimes next key locking.
How does that work?
Instead of locking the abstract predicate, the database locks the relevant range within an index that corresponds to the query's predicate. For example, if you query for meeting room bookings between 2 p.m. and 3 p.m., it might lock that specific time range in the index on booking times for that room. This prevents other transactions from inserting new rows that would fall into that locked index range, effectively preventing phantoms.
What if there's no suitable index?
If there's no suitable index to lock the range precisely, the database might have to resort to locking a larger index range, or even falling back to locking the entire table. Locking the whole table is safe. It definitely prevents phantoms. But it's obviously terrible for concurrency and performance.
Okay, so 2PL is strong but can be slow and prone to deadlocks. Serial execution is fast for specific workloads but limited. And weaker levels like read committed or snapshot isolation are faster but leave you vulnerable to subtle bugs like lost updates or write skew. This paints a somewhat bleak picture.
It does seem like a set of difficult trade-offs.
Which leads us to the third and perhaps most promising approach you mentioned, serializable snapshot isolation, or SSI. This is fairly new, isn't it?
Yes, relatively speaking.
Yeah.
It was first described in academic papers around 2008 and has since been implemented in databases like PostgreSQL, starting with version 9.1, where it's the implementation behind their serializable isolation level, and FoundationDB, which Apple acquired. SSI is gaining traction because it aims to offer full serializability with only a small performance penalty compared to regular snapshot isolation.
Full serializability with snapshot isolation performance. That sounds like the holy grail we were looking for. How does it manage that impressive feat?
SSI is fundamentally an optimistic concurrency control technique. Unlike 2PL, which is pessimistic, it assumes conflicts might happen and uses locks to prevent them proactively. SSI is optimistic, meaning it allows transactions to proceed without taking pessimistic locks, running on their snapshots, in the hope that everything will turn out all right. It avoids blocking between reads and writes, just like regular snapshot isolation. Only when a transaction actually goes to commit does the database perform checks to see if any isolation violations might have occurred that could lead to a non-serializable outcome, like write skew.
And if a violation is detected?
If a potential serialization anomaly is detected at commit time, the transaction is aborted and must be retried by the application. Only transactions that pass the checks and are guaranteed to be serializable are allowed to commit.
So it's like ask for forgiveness, not permission. What are the practical benefits for a developer choosing SSI over, say, 2PL?
Exactly, it's optimistic. The major benefit is performance, especially for read-heavy workloads or workloads with moderate contention. Because it's based on snapshot isolation, writers still don't block readers, and readers don't block writers for the most part. This leads to much more predictable query latency compared to 2PL, which is a huge win for user experience and system stability.
How does it actually detect those potential problems, like the right skew with the doctors?
It's quite clever. The core idea of SSI is detecting when a transaction is about to commit based on an outdated premise, meaning it read some information earlier in its snapshot, but that information has since been changed by another concurrently committed transaction in a way that could invalidate the committing transaction's actions.
How does it track that?
It does this by carefully tracking dependencies between transactions. There are two main situations it needs to detect. 1. Detecting reads that become stale. If transaction 1 reads some data, and transaction 2 writes to that same data, but hasn't committed yet, transaction 1 initially ignores T2's uncommitted write due to snapshot isolation. SSI tracks this. If T2 then commits before T1 commits, T1's original read is now potentially stale. SSI detects this and might abort T1 if it tries to commit based on that stale read. 2. Detecting writes that affect prior reads. If transaction 1 reads some data, satisfying a predicate like doctors on call 1, and then transaction 2 writes data that would have affected T1's earlier read, like another doctor going off call, and commits, SSI needs to know. The database tracks T1's read predicate, example via index entries it scanned. When T2 commits its conflicting write, it effectively notifies any ongoing transactions like T1 whose prior reads are now affected. If T1 later tries to commit, the database sees this notification and aborts T1.
So it's actively tracking read-write dependencies to catch those write skew scenarios.
Precisely. It tracks these potential conflicts between reads and writes across concurrent transactions. If a commit would create a dangerous cycle in these dependencies, indicating a non-serializable outcome, one of the transactions in the cycle is aborted.
That no blocking aspect sounds like a real game changer for throughput compared to 2PL.
It really is, especially for scaling beyond a single CPU core. The key advantage of SSI is that read-write transactions generally don't block each other with locks during execution. This allows for higher throughput and better multi-core scalability. And importantly, read-only queries can run using a snapshot with basically zero synchronization overhead, just like regular snapshot isolation.
Are there any downsides to SSI?
The main performance consideration is the rate of transaction aborts. If you have very high contention with many transactions frequently trying to update the same data, the number of aborts might become significant, potentially hurting performance more than pessimistic locking would have. So SSI works best when contention is not extremely high and when transactions that do need to be aborted can be retried quickly and efficiently by the application. Read-write transactions should ideally still be kept reasonably short.
Okay, that's a great overview of the different isolation levels and concurrency issues. So, stepping back, what does this all mean for you, the listener, the developer?
Well, I think the big picture is that transactions are fundamentally a powerful abstraction layer. They allow your application code to pretend, to a large extent, that many complex concurrency problems, like race conditions and various potential hardware or software faults, just don't exist.
They hide the complexity.
Exactly. A large, messy class of potential errors is reduced down to a single, relatively simple outcome: the transaction aborts. And when that happens, your application usually just needs to try the whole thing again. That's a huge simplification for application logic.
So, while maybe not every single application or operation needs the overhead of full ACD transactions, for many common complex access patterns, they're invaluable.
Absolutely. Think about keeping denormalized data in sync across multiple documents or tables, or maintaining referential integrity with foreign keys, or implementing complex business workflows that touch multiple pieces of data. Trying to handle all the potential failure modes and race conditions manually in those scenarios without transactions would be incredibly difficult and error-prone. Transactions hugely reduce the number of potential error cases you need to explicitly think about and code for.
Okay, let's quickly recap the key race conditions or anomalies we discussed and which isolation levels typically prevent them. First, dirty reads reading uncommitted data, prevented by read committed and anything stronger.
Right. Second, dirty writes overwriting uncommitted data, prevented by almost all transaction implementations. Yep, very basic protection. Third, read skew, or non-repeatable reads, seeing different data within the same transaction due to concurrent updates, prevented by snapshot isolation and stronger levels. Correct. Fourth, lost updates, concurrent read, modify, write cycles overwriting each other, sometimes prevented by specific snapshot isolation implementations with automatic detection, otherwise needs atomic operations or manual locking. A common pitfall. Fifth, write skew, making a decision based on data that becomes outdated before commit, leading to inconsistent state even when updating different objects, only reliably prevented by serializable isolation. The subtle one. And finally, phantom reads rows appearing or disappearing that match a query predicate. Snapshot isolation prevents this for read-only queries, but preventing phantoms that cause write skew and read-write transactions requires serializable isolation.
So, the big takeaway on isolation levels seems to be weaker levels like read committed or basic snapshot isolation protect you partially, but they leave you, the application developer, responsible for manually handling the remaining subtle issues like lost updates or write skew, which is hard and risky.
Exactly. Whereas serializable isolation, if you can use it, protects against all of these issues automatically, offering true peace of mind regarding concurrency correctness.
And the main ways databases provide that serializable peace of mind are: 1. Actual serial execution, single-threaded, often with stored procedures. 2. Two-phase locking, 2PL, strong, classic, but can have performance deadlock issues. 3. Serializable snapshot isolation, SSI. Optimistic, good performance, relatively new and promising.
That's a great summary of the state of play.
And crucially, almost everything we've talked about today, ACID, isolation levels, concurrency control, was mostly focused on the context of a single node database.
That's a very important point.
Once you start talking about distributed transactions, coordinating commits across multiple machines in a network, you introduce a whole new fascinating set of challenges and complexities. Things like two-phase commit, distributed deadlocks, network partitions.
Oh yes, that's a whole other can of worms. Definitely a perfect teaser for future deep dives, wouldn't you say?
Absolutely. So, wrapping up today's deep dive, The world of database transactions is clearly far from simple. But hopefully, understanding these nuances, the real meaning behind ACID, the different isolation levels, the types of concurrency bugs, empowers you to build far more robust and reliable applications.
Yeah, the goal is to move beyond blindly trusting a database's ACID compliance label. Now, you can hopefully critically assess the actual guarantees it provides under different configurations and make truly informed design choices based on your application's needs.
So, here's a final provocative thought for you to ponder. Consider a seemingly simple operation you perform in your own daily digital life. Perhaps something as mundane as liking a social media post, adding an item to an online shopping cart, or booking a calendar slot. How many hidden database transactions and delicate concurrency controlled dance moves do you think are happening behind the scenes just to keep that system consistent and reliable, potentially for millions of users doing similar things at the same time?
It makes you appreciate the complexity.
Yeah.
We really encourage you to think about the implications of these isolation levels in the systems you interact with, or maybe the ones you build every day. And definitely dig deeper into the specific isolation levels offered by your chosen database, beyond just the marketing terms. You might be surprised by the details you find.